we are going to talk some more about inverse functions today. Actually, we're not going to talk so much in general about inverse functions, but we're going to talk about one particular important inverse function. Before we get to sort of the big deal of the day, I wanted to just kind of reinforce for everybody in our minds. When you find the inverse function for another function, by the way, I meant to remind everyone, we do have homework due tomorrow. Again, check it out. One of you has already did it. Congratulations. Let me just say, concerning inverses, sometimes there's no good formula for the inverse. Even if the function you start with is something that you could sort of compute the answers of by hand, the inverse, there's no guarantee that the inverse is something that you can do at all. So for example, if I have f of x equals x cubed, then the inverse is the cube root of x, right? Now, I don't know if you feel like this is, I said sometimes there's no good formula for the inverse. This is kind of a good formula, I guess. But, I mean good, I meant to write f inverse, sorry. Can I just write this? Come on now. F inverse of x is cube root of x, right? What I mean by good formula is this. What? Sorry. You could compute this function by hand, right? If you had to, you give me any number, I can tell you what the cube is by just multiplying the number by itself 3 times. But this one here, I would just say this is very hard to compute, right? The cube root of x, I mean, we have a button for that on our calculator, which is a good thing, because other than that, it's not easy at all to find the cube root, except for certain examples you can just guess the answer. But if I ask you to find the cube root of 7, give me a few decimal places for the cube root of 7, there's not a very easy way to do that. And I myself, I never learned such a method. I know something about the history of mathematics education in America, and apparently this is something that kids used to learn how to do. When they were in school, compute cube roots by hand. Nobody does that anymore because it's pretty hard and not terribly useful. So anyway, I'm just trying to say, even if you start with a simple function, and even if you could write down what the inverse is, like here I wrote down a formula for the inverse, but this formula here is not really is not easy to work with at all if you want to actually find answers for what the cube root of something is. The formula doesn't tell you how to do that, right? Okay. Let's get down to our major topic for the day. So we are in chapter 6 of our book. If you look closely, you will see chapter 6 is organized in our book in sort of 2 parallel universes. There's 6.1, section 6.1, which is about inverses, which is all the stuff that we've done. But then there's like, it goes to 6.2 and also 6.2 star. And then there's 6.3 and also 6.3 star. And you're meant to like go down this track. This is kind of like the slightly less formal and easier track. And then this is like the real deal. This is like the PG-13 rated track, and this is like the R-rated track for people who are really serious about doing the explicit content, right? We are going to do this part over here, because this is the calculus sequence for math majors. We can handle the explicit content in 6.2 star and 6.3 star. And actually, if you look in the book, the pages for these sections are all blue, like the background of the page is all blue, I guess to indicate that you're in the parallel universe of the stars. So we're gonna do. What's that?
Said seeing the blue puts a little fear in your heart.
Yeah, maybe, or yeah, I don't know what they want it to be as not confusing as possible, I guess. So we're gonna do the stars, and anyway, all of these sections, there's 6.4 star also, I think. These are all about exponential functions and logarithms. Exponential and logarithmic functions. And this is what I said before. We're going to talk most of this class, most of our time, about a particular very important example of inverses. And they are logarithms and exponential functions. So the way that these are, I hope that you've seen something of this from high school. Although, as usual, I'm going to kind of assume that you have never heard of these things before, but I think probably you have. My experience, though, is that learning about logarithms tends to be very confusing, at least the first time around. And people learn a bunch of rules about logarithms, but sort of at the end of the day, when they tuck themselves into bed at night, they still feel like they didn't really understand anything. That's kind of how most people encounter logarithms, at least the first time around. So hopefully this will be, if it's not the first time for you, hopefully it'll begin to make some sense. Logarithms is kind of, you got to live with it for a while to really appreciate it. Anyway, the typical approach is to talk about exponential functions first, and then you make the definition of the logarithm is the inverse of the exponential functions. That's the purpose of the logarithm. And this is, historically speaking, this is how logarithms were invented. In the early 1600s, logarithms were invented by John Napier, who was a Scottish mathematician. And the way he thought of logarithms were as an inverse to exponential functions. But the approach taken in the starred blue page sections in our book is the other way around. And so what we're going to do is we will define logarithms first, and then exponential functions, exponentials, as inverses of logs. All right. Why that is because there are certain details about the exponential function, in particular the function e to the x, which you all know by now is very important in calculus. There are certain details about the definition of e to the x which are very hard to do in a sort of responsibly formal way. Whereas the logarithm is actually easier to define on its own, and then you define the exponential as the inverse of the logarithm. It's a bit backwards from the historical context, but a little more mathematically sort of sophisticated and more accurate, I would say, or easier to make completely accurate. All right, let's get right down to it. So we are going to first of all make a definition of the logarithm without ever referring to exponential functions. That's what I said here. We're going to define logarithms first and then define the exponential functions later. So how do we define the logarithm? It's based on a formula for integrals that you've probably seen before, but here's the definition. So first we define this function. We're going to talk almost exclusively about the natural logarithm, although there are other logs. The base 10 log is an important other example, but the natural log is the one that we're going to talk about most often. Here's the definition. The natural log of x, ln, which I'm going to say ln of x, is equal to the integral from 1 to x of 1 over t dt. All right, this is the definition of the natural log. It's equal to the integral from 1 to x of this function 1 over t. The way to think about this is 1 over t, of course, that function looks like this. And let me just say, this is only defined for x greater than 0. There is no such thing as the natural log of a negative number. But anyway, what this definition means is it's the integral from 1 up to x. So you start at 1, and then wherever x is, up there, say, you take the integral, this area here, that area is natural log of x. All right? That's what the definition says. So it turns out that this has a lot to do with exponents and the whatever you learned about logarithms. But this is the definition. We're going to have to sort of figure out what the connection with this and exponents is. And there are also various basic properties of logarithms that we're going to talk about. How do those basic properties follow from this definition in terms of this area? This is the definition of the natural log of x. It's the area under the curve 1 over t from 1 up to x. All right. What about, so for x less than 1, the picture looks different. Like in this picture, I drew it as if x was to the right of 1. But of course, sometimes x is to the left of 1. So let me just say when x is less than 1, it looks like we got 1 here, and then x is over here, and then the area is this, right? This area. Because of the way the integral is set up, the 1 is down here, and the x is up here. If the x is actually less than 1, then this area would come out as negative when you do the integral. And so I'm going to say when x is 1, it looks like this, and then the natural log of x is this area, but negative. All right, because when you do the integral from 1 to x, if x is actually less than 1, then the area turns out to be negative when you do the integral, if the boundary values are sort of backwards. All right. And so we can say immediately properties of the natural log, which is what I want to talk about basically for the rest of today, is just all your favorite properties of the natural logarithm. Can we demonstrate those properties using this as the definition, the integral from 1 to x? But for now, as a very sort of basic property, if x is greater than 1, then natural log x is positive. If x is less than 1, then natural log x is negative, right? If it's greater than 1, then the natural log x is just equal to this area, which is always a positive area. If it's less than 1, then you get this area, but you have to make it negative because of the way the integral is set up. What about if x equals 1? What will the natural log be if x equals 1? This is something either maybe you remember a property of the natural log because you've seen this before, or maybe not. What if this x was actually equal to 1? What would the area be there?
0.
It would be 0. Yeah, that's the only sensible thing to say. So if x equals 1, then natural log x equals 0. In other words, natural log of 1 equals 0, right? This is a basic property of the natural log function. Natural log of 1 is 0, right? Everybody knows that, right? You can check it on your calculator if you don't believe me. Okay, great. What I would like to discuss then are properties of the natural log. Properties of the natural log. First of all, let's talk about its derivative. There is a formula for the derivative of the natural log, and I will tell you, I'm going to write this kind of like I'll tell you what it is first, and then we'll talk about why that's true. This is the true fact. The derivative of the natural log x is 1 over x. This is what's so great about the natural log, or it's one thing that's great about the natural log, I guess. There are a lot of great things about this function. Let's see, can we do a little proof for this? It's not so hard. I don't know if you're into doing proofs for things. We're going to do some cute little proofs for these things in class today. The point of doing the proof, some people ask me sometimes, why we got to talk about the proof? Well, there's really two reasons. First of all, the proof suffices to convince us that the thing that I said is true is actually true. It demonstrates that it is really true. Although, depending on your disposition towards me, you might be inclined to just trust me when I tell you something. Why do I have to actually prove it to you? To make you believe that it's true? The real reason why we, in classes and also just in general, mathematicians do proofs of things is because hopefully the proof will help you to understand better what you're talking about. Not just to verify that something is true, but to understand it better. So Anyway, let's see if we can do this. The derivative of the natural log, I'm going to use the definition. The derivative of ln x, of course, this equals the derivative of the integral 1 to x, 1 over t dt, right? I just used the definition. That's what ln x means. It means integral 1 to x, 1 over t dt. What can I do with this? Anybody, does this look like anything to anybody?
It's going to sound mundane, but I'd say it looks like an integral.
Yes, it looks like an integral. I have the derivative of an integral. And does that seem familiar? Is there something you can do with this?
You can start canceling things out because derivatives and integrals are opposites.
Yeah, derivatives and integrals should cancel out. In fact, this was the sort of lesser known, often forgotten first version of the fundamental theorem of calculus. Fundamental theorem of calculus version 1, it says derivative from a to x of f of t dt. Anybody remember this? What does it equal? He just said the derivatives kind of cancel the integral. That's true, actually. What do you get then as the answer?
Just be f of t.
Yeah, you get, so it's actually f of x because this over here is the derivative using x, so the answer should be a function in terms of x. But yeah, you get f of x. And so this, I hope you remember, although it's not the other version of the fundamental theorem of calculus is the one that we use much more often. Anyway, in our case right here, what do we get? The derivative, the way you should think of this is the derivative is sort of killing the integral sign, and you just end up with the function on the inside is the answer. So here, what do we get? We just get 1 over x immediately, and that's what we wanted to show, right? I will write shewn, because that's what we were supposed to come up with. Derivative of ln x is 1 over x. All right? Excellent. Any thoughts about that one? This is the derivative of the natural log. Okay, more properties of the natural log. Let's talk about, there is a property like this. Natural log of a times b. Anybody seen this before? Remember this formula? There is a formula for this.
Is it ln a plus ln b?
Yeah, it is ln a plus ln b. I have a professor colleague in our math department who insists that the natural log should never be referred to as ln. I disagree. I don't know why. I call it ln all the time. Sorry, Sean. You can't boss me around, Sean. You're not my professor. This is the natural log of a product, okay? This is another super important property of the natural log function. Let's see. I want to talk about why it's true, and then we'll do some examples of like why it's so important and what it's useful for. So let's see if we can demonstrate this. Now, for this one, actually, we are not going to use the definition. We're going to use the derivative. So my intention is to, in this formula, sort of take the derivative on both sides. To set it up a little bit, I'm gonna write b as x, just so that it's clear. When I take the derivative, I'm using the b position as like my variable x. So I want to show, this is a typical thing that we write while you're doing a proof, is to rephrase the thing that you're trying to demonstrate in a like easier way to handle. Anyway, what I want to show is that natural log of ax equals natural log a plus natural log x. All right. And like I said, I'm going to take the derivative on both sides. So consider the derivatives on both sides. On the left side, the derivative of natural log ax. Well, I'm going to use the chain rule here. We already said the derivative of natural log x is 1 over x. So this is natural log a times x. I get 1 over a times x. And then because of the chain rule, I have to multiply times the derivative of the thing on the inside. And that is just a, because I have a as a constant in front of the x. Right. This was using the rule for the derivative of the natural log, and along with the chain rule. And then you can cancel the a's here, right? 1 over ax times a. The a's will cancel. I just get 1 over x. All right. And then what about the derivative on the other side? The derivative of the other side was ln a plus ln x. You know, of course, when I'm doing this, I am considering a to be a constant. That's why the a behaved in this way right here. I'm using the b, which I'm calling x, as the variable, and the a I'm treating as a constant. What do you think? Can anybody say, what do you get when you take the derivative of the other side? Derivative of natural log a plus natural log x. What do you say? It's going to be two parts, right? Whatever the derivative of the ln a is and the derivative of the ln x is.
1 over a plus 1 over x.
All right, I like the 1 over x. Of course, the derivative of ln x is 1 over x, right? What about ln a? He said 1 over a, but actually it's not quite that. Remember, I am considering a to be a constant while I do this, and the variable is x.
Would it be 0 then, because derivative of constant?
Yeah, that's right. It would be 0. Here I have ln a, but if a is being considered to be a constant, then ln a is just some other constant. And so when I take the derivative of that, I get 0. So 0 right here. That's because a is a constant. And so the natural log of a is a constant. And so the derivative of a constant is 0. All right. Anyway, you will notice these two things here and here. Their derivatives are both equal to 1 over x. Okay, so that means ln of ax and ln a plus ln x have the same derivative, right? Each of them has a derivative equal to 1 over x. Now, that doesn't mean that they are equal necessarily, but it means that they are different by a constant. And so we can say the natural log of ax is the same as ln a plus ln x plus some constant, perhaps. All right? If two functions have the same derivative, then they are equal, but maybe one of them is has a constant added onto it. All right? I'll say for some constant c. All right. Both sides have the same derivative, and so they are equal, except perhaps for some extra constant. And now, really, we would like to show. Remember, the whole point of what we're trying to show is that these are equal, like without the extra constant. What remains is to demonstrate or to explain why this constant actually has to be 0. Check it out. This formula is always true. If we plug x equal 1, what happens? It says ln of a times 1 is ln of a plus ln of 1 plus c. And you can simplify a bunch of stuff here, right? ln a's will cancel on both sides of this equation. These guys cancel, right? 0 equals, what is ln of 1? What's that?
0.
It's 0. Yeah, we just said that a few minutes ago. The natural log of 1 is 0, so this is going to say 0 plus c. So c equals 0, which means when you read this formula here, the c is actually 0. So that means ln of ax equals ln of a plus ln of x. And that's what we wanted to show. Right? The end. Are you into that? I don't know if you guys are into doing cute little proofs of things. The proof, you know, doesn't have any super big ideas. It's just a matter of playing around with the, in this case, playing around with the derivatives and showing that that the formula you want really is true. All right, this is a formula for adding the logs together. All right, adding the logs together is the same as when you do the log of a product. Any questions about that one? Great. Let's talk about quotients. Log of a quotient. Log of a quotient. Like this. Instead of a times b, a divided by b. It turns out this one is natural log a minus natural log of b. This is the rule for the log of a quotient. Log of a product, a times b, gives you the sum, log a plus log b. Log of a quotient gives you the difference, log a minus log b. This is how logarithms work. I want to try this one too. So this one is a little bit easier because we're going to use the previous thing about multiplication. Of course, log of a over b is the same as log of a times 1 over b, right? Instead of a divided by b, you can write it as a times 1 over b, and then you can use the rule that we talked about before. But can we just first, what about if the a and the b were the same? So if a equals b, it says log b over b, but this, of course, equals log of 1, which is 0. But also, you can break up the fraction as a product, b times 1 over b, right? This is also equal to that. And then this, we can use the previous rule, log b plus log 1 over b. So if you read this all the way across, it says, so natural log b equals, natural log b plus natural log 1 over b equals 0, right? If you read this whole thing through this way. I got 0 on one end, it equals ln b plus ln of 1 over b. Which means if I solve for ln 1 over b, it is negative natural log of b. All right. This by itself even is an important property of the natural log. But we're going to use this as part of the proof for what we want to show is that log of a over b, the thing, what it says on top, is log a minus log b. All right. Anyway, using this in the box, we can demonstrate our main thing that we're trying to demonstrate. Natural log a over b. Like I said, we're going to split it into a times 1 over b on the inside. Natural log a times 1 over b. And then we use our rule about products, ln a plus ln 1 over b. That's the rule about log of a product. But then using what I said in the box there, ln of 1 over b is negative ln b. So stick that in here. ln a minus ln b. That's the end. Right? So we are using the thing about multiplication to give us the corresponding thing about divisions that we want. All right. That's the last of these little proofs that I wanted to do for today. There's one more important, super important property about logs in the same vein here, and so I'm just going to put these all together. These are definitely formulas that you should know. Maybe I'll write them with x's and y's. As always, you can use whatever variable you want. There's that one, there's this one, x divided by y. It's log x minus log y. And then there's one more. This I don't want to go through the proof. You can do a similar sort of cute little proof of this one. X to the power r is, anybody seen this before? You know this one? I'll tell you. It's r ln of x. If you have an exponent inside of the log, you can bring the exponent down to the front. Like that. All right. So these three properties, I suppose you should definitely have these memorized. Although we're going to use them enough that I don't think you really need to. You're not going to have to put a lot of effort into memorizing them, I don't think. But these are super important. The last property there is used all the time when you want to actually solve an equation which has x's inside of exponents. The first two are used for simplifying logs in certain other ways. We can do sort of, I will say, cute simplifying of logs using these formulas. For example, the natural log of the square root of x sine x. All right. Let's try to sort of express as simpler logs. You'll see what I mean when I say what we're going to do. So this, we're going to write this, as always, the square root sign is not helpful. I'm going to write it with a 1/2 power, right? Just because that's how we essentially are always going to treat radical signs in this class. What can we do with this? We can use some of these rules here. What do you think? Which of the three rules can I use to rewrite this thing? How about someone else who I haven't heard from today? I'm not afraid to shout out the names. I will call you out.
Can you bring the half in front of the ln?
Yes, bring the half out in front. So using the third rule there, right? If you have an exponent inside of the natural log, you can bring it out as a coefficient. So this one becomes 1/2 out front, and then natural log of x times sine x. All right, and we can do even one more step, which is here now I have the log of a product, right? Here I have log of x times sine x, and so I can split that up. So it becomes 1/2, and then log of x plus log of sine x. And that's as simple as this is going to get. You can't really do anything with log of sine x. There's no cute way to rewrite that. All right, great. You'll have some practice with this kind of thing on the homework. Let's talk about more properties of the natural log. That's what we're talking about today, is various properties of the natural log. Let's discuss the graph of the natural log. The graph of ln of x. What does it look like? Now, you have to remember the definition of the natural log is this. ln x equals integral 1 to x 1 over t dt, right? This is the definition. And as far as the graph goes, we've already discussed one thing you can do if you ever don't know what the graph of a function looks like, you can always just choose points at random and plug them in and plot the points and sort of connect the dots, right? But this function is so complicated to work with in terms of plugging in actual numbers that approach is not going to work so great. Although something we know so far is something that I said before, and that is that ln of 1 is 0, and if x is greater than 0, then, if x is greater than 1, this is what I said at the beginning, then ln x is positive. If x is less than 1, then ln x is negative, right? So the graph of this function, whatever it is, and also we said we only talk about the natural log of a positive value for x. So I'm not even going to try and draw anything on the left side of the y-axis. Only positive x values. First of all, ln of 1 is 0. So where you see 1 here, the graph actually goes through that point. And then I said if x is greater than 1, then the natural log is greater than 0. That means the graph exists up here on the positive side to the right of 1. And to the left of 1, it exists down here on the negative side. I'm not saying the graph actually looks like that crazy squiggle. I just mean on to the right of this point here, the graph goes up there somewhere. And to the left of this point, the graph goes down there somewhere. So far, this is all that we know about the graph of the natural log of x. Like I said, you can't really just plug points in because this is not a formula that you can easily plug points into. Although, I'm about to tell you, there is a little trick that you can use by which you can actually plug some points. So, I will just say it this way. It's hard to plug points in order to find the graph here. Since, for example, what is the natural log of 2? That's a natural point that I would like to plug in. What is the natural log of 2? Well, it equals integral 1 to 2, 1 over t dt. But this function here is not easy to figure out what that integral is, all right? The only way you could find that integral is if you know some formula about the integral of 1 over t equals the natural log of t, but then you're back to where you started with using the natural log. The whole point is you don't know how to find the natural log of 2. I was going to say something. Oh yeah, you can, if you really wanted to figure out what this value is, you could use something like Simpson's rule or the trapezoid rule. Remember those guys? We're not actually going to do this, but you can estimate this integral here. So you could estimate it if you want to. You could use, say, Simpson's rule, etc. And the folks who invented the logarithms back in the day, they had to do something like, they didn't think of it in terms of integrals, so they weren't using Simpson's rule, but they had to use some kind of weird approximations that they did by hand very laboriously to compute certain values of the natural log. But I'll just tell you what you would get. You could use Simpson's rule or some other related techniques to find this, and you would discover that the natural log of 2, or of course, in modern times, you can just plug this into the calculator. Something like 0.693, etc. This is what you get if you tried to compute this. You could do this by hand if you really had to, using Simpson's rule. You would get an approximation. But of course, when you use your calculator, that also is just an approximation. It only gives you a certain number of decimal points. You don't get the full answer as some weird irrational number. All right. Anyway, I'm just trying to tell you, you could plug in this specific point. So where we would end up at that point would be 1 has this value, and then 2 has this weird value, 0.693, whatever. There's a point right there, all right? What about other points? You might imagine, okay, I could plug in x equal 3 and do the Simpson's rule again, but nobody wants to do the Simpsons rule even once. You don't want to do it over and over again. Check it out, though. Here's a cute trick. The natural log of 2 to the power n, we already know this rule, is n times the natural log of 2. And so that means actually I can say what the natural log of 4 is. It's, 4 of course is 2 to the power 2, which will be 2 times log of 2, which apparently is about, 1.3 something. If you just multiply this by 2, right? You get something like that. So that tells me where the value for 4 is. It's up here somewhere. All right. And you could also find the log of 8, right? This is the log of 2 to the 3rd power, which would be 3 times the natural log of 2. In fact, ln of 2 to the n, well, I already said at the beginning, it's just n times natural log of 2. This means, you can say immediately, this means as x increases, let's say up to infinity, the natural log of x also goes to infinity. That's because the natural log of 2 to some power is equal to that same power times the natural log of 2. That means as you increase this number, eventually this number will also increase. This one increases, say, much slower than the n does, but I didn't write down, sorry, I left you hanging there. I said it out loud, but I didn't write it down. As x goes to infinity, the natural log of x also goes to infinity. Of course, the typical way to write this is like this. The limit as x goes to infinity, ln x, also equals infinity. The natural log increases forever as you increase the x values. It has no horizontal asymptote. That's another way of saying that. It keeps on going up forever. And when the x is like a fraction, this thing is going to give you negative answers that go to minus infinity. And so I'm just going to say, for similar reasons, if you go through this sort of powers of 2 thing again, but using negative powers, you get this result. The limit as x goes to 2 from the right, ln x, is minus infinity. That is to say, remember, you can't ever take the log of a negative number or 0, so you can say what happens when I go out to the right, and also what happens when I approach the y-axis, and the answer is it goes down forever. And so using these basic facts as a guide, the graph looks like this. Okay, at 1 it goes through 0, and then it does something like this. It goes up forever. The way I drew this, maybe it looks like the thing is starting to level off, but it actually never levels off, although it does have, its slope is decreasing as you go off to the right, but it never makes a horizontal asymptote. It does continue to go up forever. And this one goes down forever, like this. This one goes over here, up forever. All right, this is the graph of y equals natural log of x. All right, of course you could just type this into your calculator and see what the graph looks like that way, but I wanted to give us some reason to believe that the graph actually does look like that. Any questions about this one? Great. Okay, one thing that is important about this graph is, you know, I said the values go up forever, and if you're at 2, this y value here is something like 0.6 something something, right? Whatever I said before. But the y values eventually go up to infinity. What that means is there is some sort of special point at which this y value equals 1. There has to be some x value which gives you the y value of 1. And that x value is, it has a name. So I'm going to say there is some x where the y value, I'll just say the natural log of x, equals 1. Right? This is because of the, you probably talked about at some point, the intermediate value theorem. Does that sound familiar? Since the value is 0 here, and then it goes up to infinity, like in particular, that means somewhere it equals 2. And it has to go from 0 up to 2. That means there must be some value in the middle where the y value equals 1. Right? That's the idea. There is some x value where the natural log of x equals 1, and then this is some kind of special number. It's right here. It turns out it's between 2 and 3, although that's not quite obvious just by what we know of the function, but you can compute digits of this number. This x is called e. This is one of the great sort of numbers in all of mathematics. You know, people get excited about pi because pi is kind of the basic number which arises from geometry, and it's an irrational number. The decimal digits never repeat. E is the same way. E is also an irrational number. Its decimal digits never repeat. E is, if you compute the digits, it's 2.71828, etc. There's no pattern in these digits. They're like, it's like pi in that sense. For some reason, pi has like better marketing than E does. There are a lot of people who think pi is really awesome who've never heard of E, but E is just as awesome as pi. Pi is awesome in geometry. E is awesome in calculus. All right. E, the name of it, E is in honor of a mathematician named Euler, who was the first to make a big deal out of this number E. All right. It's an irrational number. Great. Let's talk about, I want to do a bunch of examples of derivatives and integrals which involve the natural log. All right. These are, so this is the end of my sort of basic properties of the natural log. All of your favorite properties of the natural log I think I've said them, except for probably you learned some kind of what they call the change of base formula. They're logs of different bases. We're going to talk about that eventually, but not today. This is all about the natural log. So I want to talk about derivatives and integrals involving ln x, right? Derivatives and integrals involving the natural log. So the basic formula that we are going to be using is this one, right? Derivative ln x is 1 over x. All right, this is the sort of the first rule of Fight Club as far as the natural log goes. All right. What about, so we should talk about a variation on this rule. So this we use when it's just x on the inside of that ln. If you see just x in there, then you just say 1 over x, and that's it. If you see something more complicated on the inside, which is usually the case, there's some other stuff in there too. So for something like this, derivative of some other stuff inside the natural log, in this case, we need to use the chain rule. The chain rule is how you always handle something inside of something else. So we use the chain rule. And it says derivative ln of g of x. The chain rule, remember, means you do the derivative of the outer thing, keeping the same thing on the inside, and then you multiply times the derivative of the inside thing. So in this case, the outside thing is the natural log. The inside thing is the g of x. So I'm going to begin by doing the derivative of the outside, which is the derivative of the ln, makes it a 1 over whatever, keeping the same thing inside. So I don't put 1 over x, I put 1 over whatever the inside was, which is g of x. All right. That's the first part of the chain rule. That's the derivative of the outside. And then I go times derivative of the inside, which whatever that function is, you just do the derivative of that function. All right. So this is how you handle the derivative of a log with some other stuff plugged on the inside. You go 1 over the inside stuff times the derivative of the inside stuff. This is the chain rule. All right. Sometimes this is written, if you look in our book, they write it this way. Some people write it like this and then just like memorize this as another formula about the log. If you like memorizing formulas, you can remember that. I actually don't think of it in this way. Usually I just think through the chain rule. I go 1 over the inside thing times the derivative of the inside. But if you prefer, you can write it like this. This is a true fact about the log of something other than just x. All right, let's see if we can do some examples involving derivatives of logs. So just a few simple examples. How about derivative of natural log x squared plus 5x minus 1? All right. Now, you could just directly use the formula that I put in the box there, but like I said, I prefer to just think of this as a chain rule. I'm going to do the derivative of the log part first, the same thing inside, times the derivative of the inside part. So when I do the derivative of the log part, it becomes 1 over all that business. That's the derivative of the log part. Log becomes 1 over whatever. And then times the derivative of the stuff on the inside. Somebody want to shout it out? What's the derivative of the stuff on the inside? 2x plus 5, yep. Better put those parentheses if you want to write it this way. All right, and of course you could, if you want to. I would be inclined to just leave the answer like that. But if you like, you can write it this way: 2x plus 5 over x squared plus 5x minus 1. If you want to write it that way, that's fine. I would just leave it the first way around. Okay, let's see. How about another one? How about derivative of natural log of square root 3x minus 5. This one you got to do sort of like a double chain rule because I have something on the outside, the log, and then on the inside I have the square root, and then inside of that I have 3x minus 5. So this is a super duper chain rule, but I'm going to do it in the same way. First, handle the derivative of the log. I get 1 over all of that stuff. All right, so this is the derivative of the log part. And then I go times. And now I have to multiply times the derivative of the inside, the derivative of the square root 3x minus 5. Anyone want to try that out? So this is kind of a larger, but what I'm putting in here is going to be the derivative of square root 3x minus 5. Anybody into it?
Should you first change it to raise it to the 1/2?
Yeah. Think of that as 3x minus 5 to the 1/2. Huh. What you get?
Is it just 1/2 times 3?
Not quite. When you have something with an exponent of 1/2, you bring the exponent down to the front. You got to do the chain rule here. Anyone else? She said 1/2 x or 1/2 times 3, which is a little excessive with the derivatives. The chain rules. Remember, you take the derivative of the outside thing, leaving the same thing on the inside, and then separately you multiply times the derivative of the inside.
So 1/2 3x minus 5 and then times 3?
Yeah, I like this better. One thing about that that's not quite right. Anybody see something in there that's a little off? Actually, there's just something missing here.
To the negative 1/2 above the 3x.
Yeah, that's right. It should be a minus 1/2 up there, right? When I do the derivative of this outside part, the 1/2 power, 1/2 comes down front, the exponent decreases by 1, so it becomes negative 1/2. Same thing on the inside, and then times the derivative of the inside. All right? This is a little complicated. I hope this will come back to you know this sort of nested chain rule thing. This here is the derivative of the ln part, and then all of this is the derivative of the inside stuff, square root 3x minus 5. Any questions about that one? How about this? I'll make up another one like this. See if you guys can figure this. How about derivative of natural log of, let's try that. I'll give you a few minutes to try it out. It's a chain rule. You got to do the outer thing, multiply times derivative of what's on the inside. I give you 2 more minutes. All right, your 2 minutes is up. I'm going to call you out. So I hope that you should come up with something which is, again, sort of in two big chunks like this previous one. The first being the derivative of the handling the ln part, and then this stuff being the derivative of the inside. Anybody want to tell me, how did you handle the ln part, the first part here? Maybe, yes, Mr. John Kroger.
Yes, I got 1 over x sine of x.
Yeah, great. That I would describe as the easy part. The derivative of a log of something is just going to be 1 over the something. And then the inside, you want to tell me the inside part too?
Yeah, sure. I got x cosine of x plus sine of x dx.
Yeah, I like that. This is the product rule, right? On the inside, we have x times sine of x. And so when you take the derivative of the inside, you've got to do the product rule, which is, you know, the way that I write the product rule, which is what he did. You keep the first thing like it is, then you do the derivative of the second thing. So this is the first thing times the derivative of the second thing, and then plus the second thing as is times the derivative of the first thing. Derivative of x is just 1. So I get like that. Looks great. Any comments about that? I hope you put the parentheses there. The parentheses really, they do matter in this example. That it makes a difference. Here, actually, the parentheses were not necessary, but here it matters because of this plus here. There needs to be a distribution. All right, excellent. Okay, one last thing to say about derivatives, and then I want to talk about integrals involving the natural log. How about this? Here's a much simpler one. Derivative of ln of negative x. What's it going to be? Just by all the same business. You get 1 over negative x times the derivative of negative x, which is negative 1, right? The derivative of the inside here is just negative 1. And, of course, this can simplify to just 1 over x, right? This is a strange but true fact about the natural log. So, derivative of ln x is 1 over x, and also derivative of ln of minus x is 1 over x. You get 1 over x either way, right? If it's x in there or if it's negative x in there. What that means, sort of in words, is when taking the derivative of the log, derivative of ln, the sign of the inside is irrelevant. Right? You're going to get the same answer. You might as well ignore the sign. If it's a plus or a minus on the inside there, it doesn't matter. You get the same answer. What that means is we get a strange formula that ends up being important. The derivative of natural log of absolute value x is 1 over x. All right? This is because what I just said. When you're taking the derivative of a log, the sign on the inside is irrelevant. It doesn't matter if it's positive or negative. And what this rule says is you might as well just assume the sign is always positive in there, because it doesn't matter what the sign is. The derivative of the natural log of the absolute value x is 1 over x. And this formula, what's nice about this formula is this works for any x which is not 0. By which I mean any positive or negative value of x will make sense in this formula here. All right, the derivative of the absolute value x is 1 over x. This is true for every x other than 0. It's not, you're not allowed to use 0 on either side. You can't do the log of 0, and you also can't do 1 over 0. All right, and what this means, we can write this formula the other way around as an integral. So as an antiderivative formula, antiderivative here it says the derivative of the log equals 1 over x. The antiderivative will go the other way around. It means the antiderivative of 1 over x dx equals log absolute value x plus c. All right, this is the integral formula for which involves a log. This is not the integral of the log. That's something else, and we are going to talk about that eventually. But this is just the integral of 1 over x equals the natural log of x plus c. Right? And this comes up fairly often when we are taking integrals of things. Something that's interesting about this is this formula can show you how sometimes the natural log will sort of appear in the answer when you are least expecting it. Even if the thing you were talking about at the beginning had nothing to do with logs, this over here, there's no logs in this function. It's just a more or less ordinary function, 1 over x. But when you do the integral, you end up with a log. Even if you weren't looking for a log, you're going to get a log in the answer. All right. We use this often, actually, in U-substitution with denominator. So I just want to do a couple examples like this. Maybe we only have time for one. We use this formula often doing U-substitution with denominators. Check it out. Here is an integral, 3x over 4 minus x squared dx. This one we can do with a U-substitution. Now, I said all along, when you do the U-substitution, you choose the U to be the inside of something, inside of parentheses, inside of a square root sign or something like that. In this example, there isn't really much that's on the inside of something, but now that we know this rule about the integral of 1 over x, we can choose the u to be the denominator. Sometimes you want to choose the u to be the entire denominator. Oops, not D. I'm going to choose the u to be the whole denominator. Because of this rule about the integral of 1 over x, this will sometimes be a successful u substitution. So the u is 4 minus x squared. What do we get for the rest? The du will be, what do you think? What's the du here? Negative 2x, yeah. Negative 2x dx. Du is always the derivative of u. And just because I know how these things go, I'm going to divide the negative 2 onto the other side. It'll say negative a half du equals x times dx. Just divide the constant over, which will help plug things in. All right, let's plug them in. So this becomes integral. So I'm going to stick the u where it goes to begin. U was the denominator, so it's 3x over u. And then let's see if we can simplify here. I'm going to try and, as usual, separate out the u parts from the x parts. And we might as well pull the 3 all the way out of the integral. 1 over u times x dx is what remains. You separate out the fraction. The numerator can come off as a factor. And then x times dx is negative 1/2 du. So this is 3 integral 1 over u times negative 1/2 du. We can pull that constant out also, and then the substitution is complete. Negative 3/2 integral 1 over u du. All right. And we have totally substituted. It's all used now. And then what is the antiderivative? Antiderivative of 1 over u, what's it going to become? Yes, it becomes ln absolute value u plus c, using the formula at the top there in the box, ln of absolute value of u plus c. And then my very final answer is you just replace the original variable. Instead of u, I'm going to put 4 minus x squared. So the end is negative 3/2 ln absolute value 4 minus x squared plus c. There you go. That is the integral of that thing. All right. Any questions about that? Excellent. I got one more simple example, and that'll do us for today. Actually, it's a little strange, but it ends up being simple once you figure out how to do it. The integral of tan x. Everybody knows the integral of sine and cosine, but what about the integral of tangent? Tangent is a considerably weirder function than sine and cosine. If you don't already know the integral of tangent, there's not much to do with it, but actually there is a useful way to re-express the tangent. Oops. Any masters of trigonometry out there? How can I rewrite the tangent? There's actually one way that is usually helpful to rewrite the tangent.
Is that cosine over sine?
Yeah, it is. I think he said exactly this. Sine over cosine is exactly what he said. The tangent is equal to the sine over cosine. So almost always it is worthwhile to rewrite tan as sine over cosine. But now, when you write it this way, it may occur to you, I can do the same kind of U-substitution where I choose the denominator to be the U. That's what we're going to do here. So I'm going to do U equals cosine x. And then the du is the derivative of cosine. Oh, we got to go in a moment. I'll just do this real quick. Is negative sine x dx, right? The derivative of cosine is negative sine. So when I plug my stuff in, I have sine x over u dx. Split it up as I usually do. 1 over u times sine x dx. And then sine x dx is equal to negative du. There's an extra minus sign in here. 1 over u times negative du. Pull the negative sign out of the integral, and I end up with negative integral 1 over u du. You do the integral, it's natural log of u, natural log absolute value of u plus c. And then finally, we plug it in. Sorry to rush through this, but our time is just about up. Natural log absolute value cosine x plus c. Strange but true formula for the integral of tangent. It involves the natural log. So I will just summarize that. Integral tan x dx equals minus ln absolute value cosine x plus c. I don't know if you ever wondered what is the integral of tangent. That's what it is. That weird ln comes from the fact that we did a U-substitution involving 1 over u in there. All right, I think that's all I got for today. Check out the homework for tomorrow, and I will see you all in person, at least most of you, in person tomorrow at 9. All right? Bye-bye. Have a good one.
Thank you. Professor, see you tomorrow. Have a great rest of your day.
Yes.
Excited for first class in class.
Okay, yeah, it's going to be awesome.